In this second video about rectifiers, I want to concentrate on full wave rectifiers. That's circuits which give output voltages for both positive and negative going input voltages. Now, a simple passive full wave rectifier can be built with 4 diodes like this. When A has a positive voltage, the current flows around through this diode here, down through this resistor because it cannot flow backward through this diode, all the way around here through this diode and down to ground there. So the current is flowing through the resistor from the top to the bottom. That would mean that the voltmeter here would give a positive reading. However, if the input was negative, then the current would be flowing from ground back to the input A, and that current would be flowing through this diode here, around here, can't flow back through that diode, so it has to flow down through this resistor, all the way along here, and back to the input A. Once again, the current is flowing down through the resistor from top to bottom, so the voltmeter would be outputting a positive voltage. So the voltmeter gives a positive reading no matter whether A is above or below ground, which is exactly what you want for a full wave rectifier. However, we've now got twice the problem that we had before. Our output voltage, as measured by the voltmeter, is now less than the input by 2 forward biased voltage drops across diodes. We can see this when we simulate this circuit. Here I've built up the circuit, and with a 0 volts in, we get 0 volts out as expected. If I have a positive voltage in, then you can see that the output is now significantly below the input here. And that's due to the voltage drops across these diodes. Let's animate the currents, it'll be more fun. You can see the current flowing through this diode, down through this resistor, around this way. If the input voltage is negative, however, it's the other 2 diodes which are active in the circuit, and the current flows around this way. But we see a significant drop, a significant difference between the input voltages and the output voltages. For this region here, between about minus 0.6 volts and plus 0.6 volts, we're hardly getting any output from our circuit at all. And if we're trying to rectify a very small signal, which is maybe only a few tens or hundreds of millivolts in amplitude, this circuit is not going to work at all. Once again, we can use op-amps and diodes to make much better performing full wave rectifiers. This, for example, is an active full wave rectifier which doesn't suffer from the problems of the forward voltage drop across a diode. Now, it's not immediately obvious how this circuit works. The simplest way to explain it, I think, is to split it up into, first of all, just this part of the circuit here with the diodes in it. That's a circuit that I've drawn here. Now, consider what happens if A is positive. If A is positive, then we would have a current flowing through the resistor in this direction. That current cannot flow through the diode, it flows through this resistor here, round, back through this diode into the input of the op-amp. The op-amp is behaving like an inverting amplifier in the same way that we've seen before, and we would have Z equal minus A. Minus 1 times the input A. It's just an inverting amplifier with a gain of 1. On the other hand, if A is negative, then we're looking at having current flowing back through the resistor in this direction, because the op-amp is maintaining its inverting input at the same voltage as its non-inverting input, in this case 0. That current can flow through this diode directly from the output of the op-amp here, which means no current flowing through this resistor, no current flowing through this diode. If there's no current flowing through this resistor, there'll be no voltage drop across that resistor. This point here is at ground, the output will just be at ground as well. Z equals 0. Now, consider what this part of the circuit here is doing. This is a summing amplifier. You could think of that as a summing amplifier with an input here, which is Z, That's R over 2 through the feedback resistor R. And it has another input which comes from the input A. So the output X is going to be minus Z times 2, because this resistor here is half of this resistor, so the gain from Z to the output is going to be 2, plus A, because these two resistors are equal, so from A to the output, X is just going to be proportional to minus A, so we get that. Right, that means that if A is positive, X, our final output, is going to be minus 2 times Z, but Z is minus A, so that's minus 2A plus A. That's just equal to A. And if A is negative, X will again be minus 2Z plus A, but Z now is 0, so that would just be minus A. So if A is positive, the output is A. If A is negative, the output is minus A. In both cases, that would give you an output which is the modulus of A. The output would be positive in both cases, which is exactly what you want. And once again, we can test this circuit out in the simulator. Here it is. And if I change the input, you'll see that for positive voltages, the output is exactly equal to the input, with no voltage drop across the diode to worry about. And the same is true for negative inputs. The output is now minus 1 times the input, which means the output is positive. And we get from this circuit pretty much the ideal characteristic for a full wave rectified circuit. Now, there's just one other circuit that I'd like to show you. And that is a really clever circuit. Quite often in analog electronics, there are opportunities to have really good ideas and produce a circuit which works very simply, but very effectively. And you can make a full wave rectifier out of 2 op-amps and no diodes, which may sound impossible. But the trick to it is to use op-amps which are powered from a single voltage rail. So their negative power supply is ground. And you have to make sure that the op-amps are capable of outputting voltages right down to their negative rail at ground. And then you can build this circuit. Very simple, isn't it? And it works exceptionally well. Again, it might not be immediately obvious how it works. Consider the case first when A is positive. This is just a voltage follower, a unity gain buffer. If A was positive, say around 2 volts, then the voltage at the output of this buffer would also be 2 volts. The action of this op-amp is to try and keep its 2 inputs at the same voltage, so its inverting input would be at 2 volts as well, which means there's no voltage drop across this resistor, which means no current flowing through this resistor, which means there's no current flowing through this resistor either, because no current flows into the inputs of an op-amp. There's no current flowing through this resistor, there can be no voltage drop across that resistor, and the output just must be 2 volts again, the same as the input. On the other hand, if the input was negative, say minus 2 volts, the voltage follower here cannot follow that down to minus 2 volts because we're assuming that its negative power supply is at ground. So it does the best it can and it outputs 0 volts. We've now got a circuit here which is an inverting amplifier. Minus 2 volts here. This op-amp tries to keep its 2 inputs at the same voltage. This point would be at 0 volts. There'd be current flowing through that resistor from 0 volts to minus 2 volts. The same current flowing through this resistor here would result in the output being 2 volts again. The voltage drop across this resistor is 2 volts. The voltage drop across this resistor must be 2 volts as well. It's the same current flowing through them. One word of warning about this circuit though. A lot of op-amps, if they're powered from ground, don't like their inputs going a long way below ground. So you have to be a bit careful about which op-amps you choose to build this circuit, and check that they're not going to be damaged or take too much spurious input current when their inputs go a long way below their negative power rail. There are a lot of other circuit designs for full-wave rectifiers using diodes and op-amps as well. I'll leave anybody interested to do a bit of research on the internet. They all have advantages and disadvantages. That's all I wanted to say about rectifiers. Next time we'll go on and look at a common application of rectifiers, the use in a peak detector circuit.